All right, so welcome to this video. And here we're just continuing with the idea of sketching graphs. So here we've got a function x to the 4 minus 4x to the 3. So it does look like a little complex function. So let's see if we're able to sketch that. So remember, the first thing you want to do in sketching these functions is to find the intercept. Okay. So because we're in a two-dimensional space, what we'll try to do is look for two intercepts. We'll try to look for a y-intercept, and we know that that's where x is equals to 0. So let's see if we can solve that quickly. So that becomes f of 0. And according to what you can see here, you can clearly see that that gives us 0. So we know that our y-intercept will happen at the point 0, 0. The next thing we will do is to see if we can get our x-intercept where y is equals to 0. And let's see how we will go about that. So we'll go 0 equals to x to the 4 minus 4x to the 3. And then I think from here, we can safely say this will be 0. We can factorize x to the 3, which will give us x minus 4. And therefore, we can safely say from here that x equals to 0 or x equals to 4 will be our x-intercept. So that will be quite cool for us to do. Very important that we understand that. The next thing then we then have to find is to find our turning point. Okay, our turning point. And we know something special happens at our turning point is that the first derivative is therefore equals to 0. So let's see if we are able to now find these turning points. So how we will go about finding the turning points, we'll take the derivative. So this becomes 4x cubed minus 12x squared. Just using our method of getting the derivatives. And then from here we get 0. We can factorize this as 4x squared. And then we're left with x minus 3. And then from there, we can also happily say that, okay, this will equal to 0. So x equals to 0 is a turning point. And then x equals to 3. And then what we'll do just to find the corresponding y values, we'll go f of 0. And you can see we've calculated that before. F of 0 equals to 0. So therefore, we've got the point 0, 0 as a turning point. And then we will continue to see if we can get the f of 3, not the derivative. Let's see if we can erase that, not the derivative, but let's see if we can work out what f of 3 is. And when we work out what f of 3 is, this will give us 3. We have to substitute into the equation minus 4 times 3 to the 3. And if we do all of that, I think we can safely get this gives us negative 27. So this means that the other turning point that we have is 3 and negative 27. So we'll see what we need to do from there. So what I'm going to do now, just to save some space, I'm going to write the next thing here on the side. So here we want to check, we want to classify the turning point. So we want to classify the turning point. So when we classify, we then have to find the second derivative. So that's quite important for us to remember. We need to get the second derivative. Okay. So the way we will do this, we'll find the second derivative and equate it to 0 to start with. So where the second derivative is equals to 0. So this becomes 0, and this gives us 12x squared minus 24x. From here, we can factorize 12x. And this gives us x minus 2. And then from here, we can get that x equals to 0 or x equals to 2. So what does this mean? It means that we can work out f of 0 again. We know that that is 0. So this means that this point, 0, 0, it is a point of inflection. Right? It is a point of inflection. Point of inflection, and it is also a turning point, and it is also an x-intercept. And then let's see if we can get what f of 2 is. So we get that f of 2 gives us that, and therefore the point 2 and minus 16 is also another point of inflection, a POI, a point of inflection. So that does help us quite drastically. And let us see again, for the sake of space, I will see if I can work everything out from the top here. And then the next thing we then want to do, we have calculated that. We want to classify these turning points and see what they are going to be. But we know that the turning point 0, 0 is a point of inflection. So we need to investigate the turning point where 3 is. So let's plug in into the second derivative. Let's plug in 3 and see what we get. So we get, in the second derivative, we get minus 24 times 3. And then from here, we are able to get that this gives us 36, meaning that this is greater than 0. So the second derivative at 3 is greater than 0. So what this means is that the point 2 and negative 20, the point 3 and negative 27 is a local minimum. So that's quite important for us to know because the derivative is negative. So let's see if we're able to sketch these points in our graph. So here we've got the point 0, 0. We'll just space out this as 1, 2, 3, and 4. So we now have 1, we now have 2, 3, and 4. These are the points that we now have on our graph. And then we've got another point here. I'll call this minus 16. And then I'll create another point there's minus 27. So what we know for sure, according to this, is that when x is 2, we have 16 here. So x is 2, we'll have the point 2 and minus 16. When x is 3, we've got our local minimum. So this is 3, negative 27. And then we've got an x-intercept there. We've got another x-intercept there. And it's quite important for us to know because now this is a local minimum. So once we go from the minimum, we will increase our function. So we'll definitely go up from there. So our function will go that way. And because this is a turning point, and then from a turning point, if this was heading in that positive direction, it means that between 3 and 2, our function is increasing there. It's decreasing. So from this particular turning point, we can go up to this point. This will be a point of inflection. There will be some form of a curve. And this is where the graph is just going to go from being concave up to some form of a concave down again. Once we get here, we know that this is a turning point and a point of inflection. And then the graph is just going to go in that direction. Boom. So that's quite some important information for us to know. Is that in between the intervals of these functions, here we should remember that the second derivative, the first derivative will be negative. Derivative is negative. And then once we get to the point of inflection, the point of inflection does not change. It only changes concavity. So this is still negative there. And then we've got a turning point, and then our derivative is positive from there. So I hope this has created some understanding. And this is how we'll be able to sketch more complex looking graphs. You need to determine where the functions are increasing or decreasing. We will look at another function in the next video.